So we are live and we are back on our session. So yeah, once again, welcome back everyone. We now move to our next session on future fuels, new and alternate energies. We have with us Mr. Hemant Malya, Senior Program Leader, Industrial Competitiveness and Sustainability, CEEW, as a session chair for this session on future fuels, new and alternative energies. Mr. Hemant Malya is Senior Program Lead, Council on Energy, Environment and Water, CEEW. He has close to 18 years of experience in energy and environment-related issues and leads the industrial sustainability and competitiveness team. His focus areas include industrial decarbonization, hydrogen economy, natural gas systems, carbon capture, sequestration, and utilization, also carbon pricing. Mr. Hemant holds a dual MS in Industrial Engineering and Operations Research from Pennsylvania State University, USA. The speakers for the session are Mr. Hemant Malya, Senior Program Leader, Industrial Competitiveness and CEW, who will be speaking on hydrogen and derivatives. Mr. Devda Misra, AVP, Assistant Vice President and Head of Business Development, Praj Industries, who will be speaking on unlocking India's rural potential, biomass utilization for Atmanirbhar Bharat. And Mr. Jeffrey Surma, President and CEO in Entech Incorporated, who will be speaking on plasma enhanced. I hand over the session to Mr. Hemant Malya. Over to you, sir.
Thank you very much, Deepesh, and good afternoon to everyone, and good morning and good evening to folks joining from other parts of the world. So we have been hearing about oil and gas thus far, and views on alternative fuels. This is an opportunity to hear about the alternative fuels and what opportunities and challenges they pose. I'm joined by two other panelists and presenters today, Devdatta and Jeff. I'll go first, and once I'm done, I'll introduce both of them. They'll have short presentations themselves, and after the presentations are over, we'll have a short discussion. Please do feel free to put in your questions in the chat box, and we'll take it up after all three presentations are done. So with that, I'll share my screen and start my presentation, and we can go from there. Can you see my presentation, Deepesh or Devdatta, if someone can confirm?
Yeah, we can.
Okay, great. Thank you.
Yes, sir, it's visible.
Thank you. So today I'll talk about hydrogen, which is much talked about right now. What opportunities it provides, and what are the challenges specifically as they apply to India. Before I get started, a little bit about CEW, the Council on Energy, Environment and Water. Is an independent policy think tank located in New Delhi, India. We are amongst Asia's leading policy research institutions, and we work across 7 different verticals. And we also have a dedicated center for energy finance. As far as our mandate goes, we use data integrated analysis and strategic outreach to explain and change the use, reuse, and misuse of resources. That's where we operate. Having said that, let's talk about green hydrogen economy as it applies to India. So what is the motivation really? So if you look at the energy mix in India, we are heavily reliant on imports of energy. So we import more than 85% of our crude oil, about 25+% of our coal, and 55% of our natural gas. So in 2019-20 financial year, we imported almost $140 billion worth of fossil fuels. And that is a very strong motivation to try and diversify. Because as we grow as an economy, this reliance is only going to increase, and any international shocks as far as energy markets are concerned will percolate very heavily into the Indian economy. So that's a very strong motivation to diversify. Also, as we look at the challenge from climate change, there is a strong desire to not only address the energy reliance aspect, but also try and decarbonize. And there are two broad areas where green hydrogen economy can be, an opportunity. One is in industries such as fertilizers, refineries, and petrochemicals, where hydrogen is used as a feedstock already. So it's produced primarily from naphtha or natural gas and is in use as hydrogen. And then there are other hard to abate sectors where electrification is very difficult. So steel, aviation, and marine industries where green hydrogen is seen as a promising alternative. So these are the reasons why green hydrogen has gained, traction in the industry right now, both domestically as well as worldwide. So then, what are the different options for production of hydrogen? So for the uninitiated, production of hydrogen is not a new thing. In the past, coal was used to produce syngas or hydrogen through, steam reforming. That's not anymore in use. Primarily these days, steam methane reforming or SMR is in use. And that's the most commonly used process for generating hydrogen. A more recent entrant is natural gas pyrolysis, something which is again the process is not new, but then the adaptation specifically for hydrogen generation is something that is being looked at. The benefit here is that unlike in coal or methane processes, natural gas pyrolysis results in a solid carbon generation and therefore is not a direct emitter of carbon dioxide. And then, of course, there's the green hydrogen that is talked about, where electrolyzers are used to split water into hydrogen or oxygen and does not result in any greenhouse gas emissions. So if you look at the color coding, this is the general color schema that is usually talked about, green being the greenest in the sense that of not emitting any greenhouse gases, and coal and steam methane reforming having significant amounts of GHG emissions, coal being the worst of the lot. So having said that, what are the opportunities for green hydrogen in India? Like I mentioned before, refineries, fertilizers, and methanol in the country use significant amount of hydrogen, gray hydrogen, about 5.6 million tons, of which fertilizer is about 3.25 and refineries is 2.25, the rest being methanol. So this is a potential where it's a matter of switching. So as long as green hydrogen can be made available, there are no other significant process changes that are required. It's practically a plug and play solution. What we did was we tried to estimate if we had to displace this 5.6 million tons of gray hydrogen with green hydrogen, what quantum of RE or renewables would be required. So just to keep it simple, of course, there's the hybrid option of utilizing solar and wind, and that makes it very economical. But just to give a sense of what is the capacity requirement, we have only calculated on the basis of solar. So we would need about 150 gigawatts of solar capacity, about 100 gigawatts of electrolyzer capacity, and an investment of about $170 billion. So those who were listening to the previous session, the mention was about infrastructure, and the transition to a green hydrogen economy would take significant amount of investment. And just the 5.6 million tons of existing demand replacement will require about $170 billion of investment. This does not include about 1.4 million tons of fertilizers that we import. So there is some amount of embedded hydrogen in imports. So in addition to the 5.6 million tons, we can probably add another 1.9 million tons of fertilizer plus methanol import and entrenched hydrogen in it. So that's about the existing opportunities, but there are upcoming opportunities as well that can be tapped into. One of them is the steel industry. So currently, much of the steel is produced through the blast furnace route, where coal is the primary fuel. But then there is a potential to displace about 15 to 20% of the energy going into the blast furnace with the hydrogen. That provides another potential 2 million tons of utilization. Then there is mobility, especially heavy duty. So from our estimates or forecasts, we anticipate about 24,000 vehicles to be on the streets in the next 10 years, especially in the heavy duty segments and state transport buses, etc. That would generate around 0.1 million tons of additional hydrogen requirement. And then finally, there's the potential to blend green hydrogen in natural gas systems. A 15% blend by volume, given our current natural gas utilization, would result in another 0.65 million tons of green hydrogen requirement. Again, the same math as I had shown before, all of this would require another, 90 odd billion dollars worth of investment. So significant investments required even to partially decarbonize using green hydrogen. And then finally, there's the manufacturing opportunity, because if you look at the trajectory of renewables and especially solar in India, we have missed the bus in the sense that we had the opportunity to set up manufacturing in the country, and which would have provided jobs and economic growth in addition to the growth of the solar industry itself. That's something that we missed out on, but electrolyzers is an opportunity that presents itself right now, as the entire world looks at green hydrogen as a potential option or energy vector to decarbonize. So, according to our estimates, a gigawatt of manufacturing capacity requires an investment of about $67 million. And if we have to replace or add to the green hydrogen requirement, as I showed previously, of about 10 million tons per annum by 2030, then we need a electrolyzer capacity of 180 gigawatts by the end of the decade. And this would require an investment of about 1.2 billion annually, assuming that we deploy evenly 18 gigawatts, each year. And then there is the aspect of how much of the content can be domestic, because from an economic perspective or jobs and growth perspective, this is an important factor. And our research and analysis shows that about 84% of the value addition in manufacturing an alkaline electrolyzer can be indigenized. So there is the scope of value addition to our economy as well, in addition to creating the decarbonization opportunity. Finally, there is a lot of potential for export of electrolyzers, as well as green ammonia, which is a derivative product from green hydrogen, because a lot of countries like Japan, Singapore, and South Korea are looking for imports of green ammonia, given their own renewable energy potential is significantly lower than the energy consumption they have internally. So that opportunity also presents itself. So having said that, why do we think that green hydrogen is a potential solution? So if you look at the solar story in India, the blue line on the chart shows the solar tariffs over the last decade, and the orange line shows the installed capacity. So as the capacity has installed capacity has increased, the tariffs have fallen precipitously, and we anticipate something similar to happen globally, because the capacity addition for electrolyzer manufacturing is picking up pace. That is what resulted in the installed capacity for solar also to increase in the past. So right now, in the batch process mode, electrolyzers cost about $700 to $800 per kilowatt. That was as of last year. But given current manufacturing capacity addition, which is a continuous process, and at a giga scale, already we are looking at electrolyzer prices within the last year to have fallen to around 400 to 500 USD per kilowatt. And in the future, there are targets to reduce it even further by half. Again, it's going to be a function of technology as well as scale, but that would result in a similar trajectory that we saw on the solar tariff. So although it might look challenging right now, we are where we were 10, 15 years ago on the solar story. The other aspect of why we feel hydrogen economy might be on the rise is because of the government's intent to make it possible, and that is important to create the right signals in the market to enable all the right market players to invest and to project what they can provide in terms of the ecosystem build-up. So one of the features, and all of this is in the public domain, I've tried to just summarize it. But the National Hydrogen Mission tries to address both the existing as well as new opportunities for utilization of green hydrogen. So it spans across multiple use cases. It also intends to put some purchase obligations on end users, and that's a very strong signal for the supply end, because it ensures offtake guarantees and helps de-risk their investments. Further, there is the intent to provide PLI schemes for electrolyzer manufacturing. Again, the manufacturing domestically will provide both scale as well as cost advantages, not to mention the job and growth potential domestically. And then finally, the government intends to get involved in the bidding of the green hydrogen procurement itself. Now that's a another strong signal, because 45% of the demand that I showed previously is from PSUs, and therefore it's easier to implement these mandates if the government gets involved in the bidding process. And finally, at least in terms of the early indications, there is the potential for provisions on blue hydrogen. So it's a primarily green hydrogen mission, but there might be a possibility of incorporating blue hydrogen in the larger scheme of things. So that's again a good signal from our perspective, because green hydrogen, all said and done, will take another 5 to 10 years before it picks up. But blue hydrogen, especially from natural gas pyrolysis, has the potential to scale up the ecosystem fairly quickly, because we already have natural gas imports and an infrastructure in place. So having said that, it's not all a rosy picture. There are challenges in adopting green hydrogen. And the chart you see on the screen is essentially the breakdown of energy consumption in the country. It's a slightly old data set, 2016 or so, but I think it's sufficient to make the larger point. So the x-axis represents the petajoules of energy consumption of each fuel type, and the y-axis is the delivered price of that fuel. So you can see coal is by and large the largest energy source for the country, and it's dirt cheap. So right now we are looking at green hydrogen prices of around $4 a kg. But even with $2 a kg, it will barely break even with some of the most expensive fuel. In this case, coal and lignite products, which is nothing but coking coal and briquettes, etc. If we have to decarbonize significantly, we'll have to go sub $1 per kg to match up with the price of coal and lignite that we see in the markets today. Now, this is purely on a commercial basis. Of course, any kind of carbon market will change the equation, given that there'll be a price on the carbon for each of the fuels. The other point I wanted to make was, if we have to hit sub $1 per kg price on green hydrogen in the next decade, which is commonly now known as the 1-1-1 target, which is sub $1 in 1 decade. There are some underlying metrics that we'll have to hit. So solar power right now is around 2.25 rupees per unit. It'll have to go around 1 rupees per unit. Electrolyzer costs, which were until last year about 750, now we are talking about 450, will have to dip down to $200 per kilowatt. The stack life of the electrolyzer will have to essentially double, and the efficiency will have to go up from around 67% average right now to about 80%. So significant challenges do lie ahead as far as the technology is also concerned. So we are not yet there. It is promising, but the challenges still exist. There are other non-technical challenges as well, such as policy coherence. So we know that it's cheaper and more efficient to wheel power and generate green hydrogen in a distributed manner. But our power system or power markets are highly convoluted. There are many legacy issues which make it very difficult and expensive to transport power. So then the question is, are we going to wheel power or transport hydrogen through physical, pipelines or other means of transport? So there's no policy direction in that sense. The same applies to something like hydrogen versus EV for heavy duty transport. So both have been talked about as being promising, but then the policy has to be very clear on which one is favored and where and why. That is not in existence right now. Then there is the infrastructure readiness challenge. Gas pipelines today are primarily structured to carry natural gas. Hydrogen results in embrittlement, or it eats into the steel because of the quality and grade of steel that has been used in the past for carrying natural gas. So there is the possibility of adapting our infrastructure to hydrogen, and here I'm talking about 100% hydrogen, but then there is a cost associated with it. So the question is, how are we going to reach to a point where the adaptation happens, and the other question, who pays for it? Then there is the question of grid reliability and open access. Open access I talked about, but then grid reliability, if you're looking at green hydrogen and wheeling power to generate green hydrogen, There is a question mark on whether certain sections of the grid are able to handle the quantum of renewable energy that would be required, given the intermittency that we'll also see. And then, of course, there's a question of storage, because renewable is not available 24/7. End user readiness is also a question mark. Some end users are probably more ready than others. A good example is a piped natural gas in homes. There is, no clarity on whether the stoves that are used in home for cooking, the burner tips can handle, larger quantums of hydrogen beyond the 15%, 20% that is being talked about. So, any such change in or increase in hydrogen blending and natural gas will require huge amounts of, infrastructural changes. That is something that has not been studied and needs to be looked at. Then there is the competition from other alternatives. So green hydrogen is not the only solution to decarbonize. Much has been talked about carbon capture, utilization, and sequestration, or bioenergy options, which my co-panelists will talk about shortly. And the economics of these alternative options have not been weighed against green hydrogen on an end use by end use perspective. That's something that is still pending and needs to be done. And then availability of finance. Like I mentioned earlier, about $200 billion required just to cater to 10 million tons of green hydrogen. And so where is the finance going to come from? And even if it comes, what pace does it come at to enable us to rapidly grow the hydrogen economy? The scale of RE deployment is unprecedented. After a decade plus, we have hit 100 gigawatts of renewable capacity only recently. Just to give a sense of scale, if we had to replace the 110 million tons of steel that we produced with green hydrogen-based green steel, we need a RE capacity of around 265 gigawatts. So that's only steel. If we had to decarbonize other sectors, as well as use hydrogen for storage, etc., we're talking thousands of gigawatts of renewable capacity. Again, an unprecedented scale, something that has not even been planned before, and will be a big challenge. And finally, the aspect of just transition, because fossil fuels aren't merely a source of energy, but they also, the entire supply chain supports a lot of jobs across the value chain, and any switch in the type of fuel we use as a country will require that there is repurposing of the infrastructure, but also reskilling of the employees in this supply chain. So that will act as a barrier if not addressed. So those are the challenges that we foresee as far as the green hydrogen economy is concerned. So that's it from my end. CW has published several publications on green hydrogen, and there are many more in the pipeline. Do invite people to visit our website and peruse of those documents. So with that, I'll stop my presentation and invite my co-panelists to speak. Next in the queue is Devda Misra. And Devda is heading the business development of CBG division at Praj Industry, where he has been working for the past 4 years or so. He holds a mechanical engineering degree and also a management degree from IIM Calcutta. He has more than 18 years of experience working in the renewable energy, power sector, steel, FMCG, and chemical sectors, where he has worked across business development, strategy, and supply chain issues. He's also a mentor at the Startup Innovation and Incubation Center at IIT Kanpur. With that, Devda, I would like to invite you to make your presentation, and we'll go from there. Thank you.
Yeah, thank you, Hemant, and very good evening to all of you. Just I'll share my presentation. Just a second. Is it visible?
Yes, please go ahead.
Today I'll be speaking about another renewable form of energy. And I think today's sessions are all around futuristic energy potential that we have in hydrogen. But today I'll be more talking about biogas or compressed biogas as another form of renewable energy and how it is helping India right now. So I'll start with the subject that we talked about, transportation. Now, if you look at the transportation and the energy requirement in transportation as a overall worldwide, we are almost using 21% of the entire energy basket. Now we are looking at making the entire transport sector transiting towards renewable energy or adapting towards renewable energy. And I'll be talking more about how we can utilize our waste and convert into a renewable form of energy, and so that we can utilize in our mobility systems or transportation. Today, we can actually use a lot of variety of waste and convert into many different kind of energy, be it liquid form such as ethanol, 1G ethanol, 2G ethanol, even biodiesel, or even gaseous form that I am talking about today is CBG or BioCNG. Even we can produce jet fuels, marine fuels, and biohydrogen also from these feedstocks. And with all this possibility, today, actually in Praj, we have already commercialized some of these renewable fuels, such as ethanol first generation and second generation. Even CBG we have commercialized, and we have been building around other waste to energy platforms as well. Now coming to, because this session I would be limiting myself to only the CBG. What is CBG? CBG is nothing but the renewable biogas or renewable bio-CNG. This, in terms of molecular level, if you look at it, is almost identical to natural gas. But the only thing is, in India, when we are producing biogas or the bio-CNG, the methane percentage is almost as high as 96%. So it is actually a higher methane content molecule than natural gas. So in terms of calorific value, it is higher than the currently available natural gas. Now, if you look at how this biogas is produced, and we have in India a lot of different feedstock. Any organic waste material can be used as a feedstock to produce biogas. And this biogas is an anaerobic process, digestion process. And after this anaerobic digestion, the biogas that comes out is typically 55 to 60% methane content in it. So we need to purify it further to make it 90%, 96% pure. And this purified form of methane, then compressed, and then for transportation we use cascade form, as as we're currently doing with the CNG also. And this biogas or bio-CNG can be utilized in many industries, be it power application, vehicular application, even industries, home application. Wherever we are using currently natural gas or CNG, we can utilize this. And now coming to, we know that India has already taken a target to increases gas in the energy basket from 7% to 15%. So we see the entire infrastructure development around gas sector, and in that we are also targeting 5% renewable of the overall gas that we will be going to use. So we're talking about a 5% blending in the entire gas. So looking at this, we see there's a lot of potential. Now I'll come to the potential of biogas or bio-CNG that is existing in India. If you just map the entire raw material available, the waste that is available in the right pie chart, you can see that the current available waste can produce as high as 62 million metric ton of CBG or the CNG, bio-CNG per year. Currently, the India consumption is around 50 million metric ton. So in terms of availability, the potential of generation of CBG is huge, that we can entirely substitute the current gas consumption. But if you look at the which kind of feedstock we'll be able to use in India, and we compare with the worldwide scenario, you see the worldwide left side pie chart, you can see the biogas that comes from in a world scenario, you can see that is dominated by farm waste, or it is dominated by the agri residues. Most of these are energy, grass, or corn silages. But typically in India, the pie is different. what we see in India is there is a lot of potential from surplus agri residue. We talk a lot about paddy burning issues and all those surplus paddy residues are there. So that consists of a huge chunk of our potential. Apart from that, there are two other easy feedstock that we have, because we have a lot of sugar plantation around our country, and 400, 500 sugar plants are there. So sugar plant waste, which is called press mud, spent waste, and bagasse, and the MSW, the municipal solid waste. So combine these three forms a major chunk of raw material which can be easily converted to CBG. There are other ways such as farm animal. We have a lot of cattle animal population, but the challenge in India is we have very don't have bigger farms. These are all animal population is distributed among many farmers. So collection is a very difficult issue here. So even if we have a cattle dung availability, but we don't see a lot of commercially viable bigger plants can come up from this feedstock. So this is some of the changes when you see from a world perspective versus India perspective, and this is very. If you look at the raw material availability, also most of the feedstock will be available in rural areas. So that is another dimension. Now I'll talk about, we speak a lot about when we're talking about a newer form of energy, how it is viable. So I have just plotted a graph of current, whatever we are using as different fuels for our transport application. If you look at the current retail prices, and you can see the retail prices of gasoline, diesel, or whatever we have, versus you compare with CNG, LPG, or CBG, the compressed biogas or BioCNG, you can see that the BioCNG is actually having the highest calorific value if you compare on a calorific value scale. But currently the market prices are almost the minimum among all the fuels that we are currently using. And when you compare it with the dimension of cleanness or clean burning, this CBG, the amount of CO2 that gets generated on a life cycle basis is almost 1/4 that of their non-renewable fuels. So you can see that Indian perspective, this is an Indian scenario. So there are many dimensions why the other prices are very high because of there are inherent taxes in it. But on a retail space as it is that we stand, the renewable energy from BioCNG is not only having higher calorific value, but also the cheaper as of now. Now coming down to, we talked about that there is an absolute high amount of raw material that is available. From a market perspective, we don't need to incentivize because it's already, the price at which it is selling is almost equal or even lower than other peer fuel that is existing. Now let us look at the technology perspective. Now the technology of biogas generation is there. It is not, you can go to Europe and US, other part of the world, and there are so many plants already running. So technology is existing. There's nothing new in the technology, but what is new is from an Indian perspective when we have to look, and because some of the feedstock are very new, which is not available around the world. For example, this paddy straw that we're talking about and is a inherent problem in India scenario, it is not there worldwide. And Indian variety of rice comes with a lot of inherent silica also, which is very difficult to process and it has own challenges. So in that perspective, yes, the technology needs to be built around Indian perspective, keeping that in mind. And also some of the feedstock, for example, when I go into technology, there are 4 different dimensions to technology development. One is what kind of pre-treatment we do. Second is around the entire biomethanation process. Third is gas purification. And fourth is organic manure. So when we talk about the technology around pre-treatment, as I said, this biomass, when it comes to paddy, we need to look at the processability of such feedstock, how we are going to handle such feedstock, and then how we are going to break the bond between cellulose and the lignin, how we can improve the yields, how we can make it more homogenized and slurry form so that it can easily goes into the process. So all these things comes into picture, and that's why the pre-treatment process is very critical. And in Praj, we have developed a microbial pre-treatment around this process, and there are many other forms of pre-treatment available. Some use enzymes, some use harsh chemicals. But this is very critical. Pre-treatment process is very critical. Similarly, if I can give another example of pre-treatment, for example, let's take a raw material of press mud, which is a sugar plant waste, which is easily available in abundance. So there also the challenge is in India, the sugar season is only 5 months. Typically around the world, sugar seasons are high 9 months to 12 months, but in India it is typically 5-6 months. And then the challenge is how to preserve it for around the year so that I can make a plant and run the plant around the year. So around that also we have created a pre-treatment process where again we use microbes to stabilize the entire feedstock and store it around the year without any yield degradation. Now coming to biomethanation, there are many technologies available, different designs available, but primarily the designs that currently in market they're using is either CSTR design or a dual plug flow design that we are currently proposing for all solid feedstock, because we see that it is more rugged in nature, no breakdown and maintenance requirements, and higher yield and degradations. So, and third aspect is where once we get the biogas, how to purify, because if you are going for a pure power application, you don't need to do a lot of purification. But if you're looking to use it in a vehicular application, the stringent purification requirement is there. So that's why this purification process is critical. But there are so many different type of technology already available in commercial scale that in India also now it is there. So I don't think this gas purification process is anyway of any from a technological perspective it is available. Now coming to the fourth aspect, so these all CBG plants, they also produce a lot of organic manure. Government of India has already certified that whatever organic manure is produced is already certified under government schemes. And now these, because these plants will be coming in rural areas, so these organic manure also will flow back to the farmers where they can replace it with their existing chemical fertilizers. And we have seen excellent result in our existing plants. And these organic fertilizers or organic manures also are rich in fixed carbons, which is a critical requirement as of now in the soil. So in nutshell, just to give you an overview, that technologies are available. Of course, the refining is there, some fine tuning is going on, but technology is always available. I'll just, this is my last slide, and then I'll just narrate what is happening in India from a BioCNG perspective. From 2018 onwards, Government of India has already created a program where they have a vision to build 5,000 CBG plants. But in reality, today we see 20 odd plants have come, and we ourselves are building 6 to 7 plants out of it. So from a policy perspective, government have done fantastic job in the sense that within 2 to 3 years, they have actually, came up with all those policy and implemented. It's very nice implementation over there. If you look at even the rice straw that were the difficult feedstock, I would say in India. So there are also 3 commercial plants have already come or underway. So this is also a good news. And after this is first wave of reference has come, then suddenly we'll see a spike of that. So in nutshell, if you see that these CBG plants are not only utilizing the waste or reducing pollution, in terms of reducing this paddy burning issues and all, but also it creates a local employment because these are all set up in rural areas. And of course, this reduces import bill and all those things for any renewable energy form. And more or less, this also promotes indigenous technology because these technologies are not very complex in nature. So a lot of indigenous players are coming up with that technology. And we can see this is a true example of circular economy because everything comes from India and then we're utilizing that. And we call it Atmanirbhar Bharat or self-sustaining India. So that is a true example of that. Only one thing I would like to add to this, that still with all these benefits also, this sector itself is in a nascent form. Just started 2 years back. Still needs some kind of support from financial feasibility point, and that we see that government is also stepping in, and we see other players are coming up. So we'll see in future that it will take off. So with this, I'll stop here. I think I have exceeded my time. Any questions, I'll be free to happy to answer that. Thank you.
Thank you, Devda. Maybe you can stop sharing your screen, and I'll invite Jeff Surma now. Good morning, Jeff.
Morning.
Jeff Surma is the president and CEO of Inentech. Prior to joining Inentech, he was a senior research engineer at PNNL, Pacific Northwest Laboratory. I think everyone knows that, where he led a multi-million-dollar research project in the area of high-level radioactive waste vitrification, electrochemical and plasma processing of waste. Subsequently, he led a multi-institutional team involving PNNL and the Plasma Fusion Center at MIT to develop plasma technologies that have since been commercialized through Inentech. Mr. Surma holds 45 patents and also holds several international patents, and has won the prestigious R&D 100 award 4 times thus far for his work on plasma processing and associated technologies. Jeff holds a BS in chemistry, from the University of Minnesota, and an MS in chemical engineering from Montana State University. With that, Jeff, please go ahead. The floor is yours.
Very good. Thank you. Can you?
Please go ahead.
Very good. Well, again, thank you for having me here. I'm really pleased to be part of this. So today I'm going to what we call our plasma enhanced melter, but it's a recycling technology that recycles at the molecular level and converts almost any waste material into low or negative carbon syngas, hydrogen, other clean fuels and chemicals, and helps to advance the decarbonization of the world's industries. A little bit about Inentech first. Inentech is headquartered in Washington State. We're built on about $300 million worth of federal, where we conducted a significant amount of work both at the MIT Plasma Fusion Center and at the Pacific Northwest National Laboratory. We've recently been highlighted in MIT's Energy Initiative and NASA's spin-off magazine. So the technology itself is based on two different technologies. One, and you heat that molten bed of glass with alternating current, forming a lava-like substance within this reaction chamber. Above that reaction chamber, you establish a plasma arc zone using direct or DC power. That direct DC power forms very high temperature plasma arc, about 8,000 to 10,000 degrees C. Any material that enters this arc zone breaks down into its elements and reforms into very, very clean syngas, CO and hydrogen, with, of course, a little bit of CO2. Anything that would be ash in an incineration process turns into glass. And if there are any metals, it just is tapped out as a separate metal phase. We then combine that reaction chamber with a co-current downdraft gasification unit, which we call our pregasification, our initial gasification stage. In this chamber, we control the extent of reaction using an active grate system so that the material passing through here is only gasified, maybe 65 to 75% of the incoming material is actually converted into syngas, and the remaining char-like material falls into this plasma zone. What that does is that enables us to use the minimum amount of electric power that's required to operate the plasma portion of the process. and still get the benefits of the plasma having the ultra high temperature and very clean syngas production. So the waste material enters in the top. We go through the pregasification stage, the plasma stage, and then out through a thermal resonance chamber where the gas just stays at temperature for a predetermined period of time. Normally, that's about 2 seconds. The systems can be modularized. In fact, we are working with Praj Industries in India to modularize all of our plants. The standard module is 125 to 150 ton per day processing capability. That's input waste, depending on what the waste material is, either MSW, municipal solid waste, or biomass. And of course, then you can hear this 3D image is from one of the plants that we're working on in California for conversion of biomass into renewable green hydrogen. The environmental performance of a process like this is very, very clean. This is data that we generated while working with Kawasaki Heavy Industries in Japan. We fed, in this case, a toxic material, polychlorinated biphenyl material, which used to be used in transformers. This material was processed in our system in conjunction with the and basically we were at detection limits for the analyzer, indicating that none of the dioxins or furans were coming out of the system. And we had 9 to 10 nines destruction efficiency. So moving on to where Innotex technology address some markets to decarbonize world industries. You've heard about biogas. Here in this case, we're talking about syngas produced from a variety of waste streams. First, we address the distributed hydrogen market, and I'll talk about that in just a moment. A very big problem that the world has, and then of course just various forms of renewable fuels and energy. A distributed hydrogen facility using Innotex technology was constructed in the state of Oregon. It's 25-ton capability of input waste. It's designed to handle medical and industrial waste, but it has mass, can produce 700 to 1,500 kilograms of hydrogen per day. And this is fuel cell grade hydrogen. So we have enough hydrogen to fuel 1,500 to 2,000 cars per day. Has a very small, and this model can be used or replicated in a distributed manner. This is the gasification unit that I showed you before. The raw syngas goes through a quench. We remove the particulate. We run it through a wet gas scrubber to remove anything like chlorine gas. For removal then is followed. And finally, we go through some garbage to remove any trace, maybe part per million compounds. And then the syngas to shift any of the CO to CO2 and more hydrogen, pressure swing absorption system to hydrogen, the purified fuel cell grade hydrogen, and then of course the final delivered hydrogen. The tail gas goes to a thermal oxidation process for steam or power production. Our hydrogen production costs negative raw material input cost. So we can actually produce hydrogen at a negative cost. So this is a very desirable situation as we try to move to the hydrogen economy when we can compete with the production of hydrogen even from natural gas using steam methane reformers. The plastics is something that all of the chemical companies that generate plastic products are very interested in. There's over 300 million tons of plastic produced every year, and only about 7% of that's recycled, with 8 million tons ending up in our oceans. So with plastic circularity, Inintech's technology enables what otherwise would be impossible to recycle plastics and divert them from landfills and process them into high purity syngas, hydrogen and CO, or pure hydrogen, or other fuels. And we're looking at a number of options in that area. So the various renewable products that we can produce in the areas that I just described, of course, hydrogen, ethanol, we're using LanzaTech's back-end technology to produce ethanol from our syngas, methanol. Renewable DME is a new market that we're moving into in a very big way. Renewable natural gas using methanation reactors. We're working with another company called Bluescape Clean Fuels to actually make drop-in renewable gasoline directly from syngas, and then of course power generation. Some examples of commercial facilities. Here's one of our facilities for chemical waste processing. This is the hydrogen facility in Oregon. This is a medical waste processing unit in Taiwan. And this was the plant that we used to generate that data that I described earlier with Kawasaki Heavy Industries. And then we also can produce small systems. This is a mobile unit that has a small capacity, but is used for either disaster relief or gasification demonstration projects. So in summary, plasma system is really applicable to a wide range of feedstocks, including biomass, has a flexibility to produce a wide range of energy products, including hydrogen, and that hydrogen can be produced at very low cost. The PEM process combines the advantages of both plasma technology and traditional gasification technology, which makes it really robust and cost effective. And then we also have the ability to produce value-added glass products from the glass that is produced, where we would otherwise make ash in an incineration process. We have high-value glass products that can be produced. The PEM systems are modular in design, so it enables scalability both up and down, which is important for distributed hydrogen facilities on a smaller scale, producing gaseous hydrogen. In fact, so with that, I will end my presentation.
Thank you, Jeff. We don't have any questions thus far, but I guess, I have a few questions, so maybe I'll go ahead and get started with that conversation. So Jeff, very, very interesting technology. One of the challenges that we see in India, which may not be the case in other parts of the world, is waste segregation is a huge problem. So, in our case, organic, inorganic waste gets commingled, and separation, if required for any kind of processing, adds to the cost, given the volumes that we generate. So the question I had was, I guess a couple. One is, does your technology require waste segregation? That is one. And then I guess a related question is, how scalable is it, a modular technology? Because just like we have biomass, waste is, all over the place, and collection of waste is a cost again. And so, how modular and distributed can your system be?
Yeah, so the answer to that is absolutely. We can take a diverse and heterogeneous waste stream. There's no segregation of the material required at all. It showed in the diagrams of the modular plant. Like I said, we were working very closely with Praj Industries there in India so that we can distribute, put them out in a distributed manner, much more cost effective. And in fact, that is our desire now, is to move to a lower cost modular plant specifically for markets like India, where you may not need all of the features of our system that can handle this wide range of materials like plastic and chemical waste, but rather focus on some aspects of the municipal waste stream.
Sure, thanks. Devda, I was looking at your presentation, and one of the slides you showed was very interesting, where on a commercial basis, CBG achieves parity with other streams of fuels, and especially CNG. So is that number of 55 inclusive of some kind of financial support from the government, or is it a standalone based on a purely commercial venture? And if so, my question is, we have about 200 million tons of biomass only, not to mention the 275 million tons of waste, etc. So huge potential, right? So how do we, and yet the target for 5,000 CBG plants, only 20 or so, in the pipeline. So, what are the challenges, both from an operational perspective, as well as the commercial perspective? Is there any hope to commercialize the CBG technology or the technology that Jeff mentioned purely on a commercial basis?
Yeah, I think it's a very good question. I'll take some 5 minutes of your time to give answer, because there is no single answer to this. But the first point that you mentioned, that the retail price. Interestingly, I think you also showed a slide where you showed that when solar industry started, the PPA's price was very high and slowly it reduces. Similarly, cogen industries and so many industry which are renewable, government gave prices actually on a PPA basis. But interestingly, or maybe for this CBG sector, so for the price, there is no actually incentive for the selling price or the product that we're selling. There is actually no incentive. Mm-hmm. One incentive that government came up was to buy this CBG at a price of 46 rupees. If you buy at 46 rupees with all this GST transportation, it's still at 50 to 53 rupees retail price. Mm-hmm. But actually, if you see that still it is the cheapest on a retail basis, it's still cheapest, and the calorific value basis is still the best among what is available today in India. From a market perspective, it is actually we don't need any subsidy from market price perspective. That is for sure. But having said that, why, as you rightly said, why these plants are not coming? We have the waste, we have the technology, price point is good. Then why it is not coming? There are many other actually factors to this. I'll touch upon 2 or 3 factors that are critical. First factor is when it comes to some of the critical feedstock like biomass. Now for biomass, we have a surplus biomass availability. We're actually burning it. But as I said, from a technology perspective, there is no reference worldwide, and we are slowly creating references here. So that is one point. Second, from a logistic perspective, though they are burning, but when you are actually going to, aggregate and going to take those and try to put an infrastructure actually to aggregate, there are so many middlemen, and the landed cost of those raw materials are increasing, which is creating a impact on the feasibility. And third aspect is overall viability of the plant. See, currently there is absolutely no financial support because there was a support from MNRE which was still not extended. So today we can actually say there is no financial support for this kind of a project, which makes us, you can imagine any renewable project standing on its own without any kind of financial support. In the initial phase is difficult, but slowly we'll have all the developments in technology and other things to come. But today there is a challenge. And last thing is challenge around, there are so many people who would like to actually put up such smaller plants, but they're not getting funding because even the banking system and they're not financial institutions, they're not ready to fund because they don't see the reference. They don't see any actual plant running So slowly, today we see that first batch of 10 or 20 plants have come. They are now started operation. That gives kind of reference and kind of feeling to bankers that yes, it can run profitably and government policies are stable. Slowly it will come. And like I said, some of the feedstock are available, but not aggregable. So we have to let go of that. And some feedstocks are also available, but at high cost. So it doesn't make sense to convert to CBG. So we are only targeting, like I said, biomass, press mud, and MSW. These are 2-3 feedstock which we are targeting, which will be financially feasible to set up such plant at higher scale.
Sure.
So I
thank you.
On 2-3 points. There are many.
Yeah. So essentially, it's a cost of capital, supply chain, issue, and just the fact that you don't have the scale yet. Is that summing up?
Yeah, and one more aspect is, like I said, today it is rural. All these plants is coming in rural areas where we don't have a CNG presence as of now. So there is absolutely no grid or absolutely no vehicles to offtake on the day zero basis. There is a feeling that there is a policy that government OMCs will buy, but there is no take or pay. So people are actually waiting to see first couple of plants come up and see how it is performing. And we're happy to say that our first plants from day zero, we have seen offtake happening, 100% offtake happening. All the organic manures, there is a huge demand from the farmers, which they are so happy that they are queuing up for taking that. So these success stories will slowly build, and number of plants will come. And of course, some amount of support, financial support from government side is also necessary in the initial phases. So that.
Sure. Jeff, a question I had was, you mentioned waste in your process, but what is the ability for it to handle something like biomass or, forest residue or industrial waste, etc.? You're on mute, by the way.
Sorry. Yeah, absolutely. No, I mentioned that we have a plant in the Central Valley of California here in the U.S. That plant is being designed specifically to process biomass. And so the technology works well on biomass. In fact, we demonstrated for that particular customer the conversion of biomass into very clean syngas that then can use the LanzaTech backend process to produce ethanol. And it is cost effective. It depends, of course. Here in the U.S., ethanol has a lot of subsidies, so the economics work very well in the U.S. We're looking at a number of new projects, biomass, green waste, as well as the biogenic fraction of MSW to produce renewable methyl ether.
Sure. Since you mentioned LanzaTech, this is a question I have to ask to both of you: is what is the potential for integration with other, so-called green technologies? For example, can there be an integration with the carbon capture systems on the one hand, or with green hydrogen on another? So both of you, if you can take this question and kind of expound a little bit more on that. Maybe Jeff, you go first.
Okay. One of our projects right now, we are looking at carbon capture and sequestration. That's the same project in Central Valley of California. But some of our other smaller projects, we are evaluating technologies that are out there that can operate on a small scale to affect carbon capture.
Okay.
Yeah, so I'll give a little different answer here, because as an intermediary, yes, methane can be used to produce hydrogen. But I can't say as of now how viable it will be, but as if intermediary, yes, the pathway is there. If somebody wants to build green hydrogen based on green methane or biomethane, it is possible. But coming to CO2, I would say that in India, still there is a demand of CO2 and we don't need to, we can capture and utilize in different forms. And we do that. I mean, in our ethanol plants also, there are many plants where we use capture and use CO2 in good use. So in our plants also, if there is a sizable capacity, we can definitely use this, capture this CO2 and use it, bottle and use in liquid form. So there are many, as of now, demand is there. We don't need to, sequester it as of now. But if there is a very big plant, I mean, we don't have that much demand, then yes. But technologies are available.
Great. Well, those are the only questions I had. We don't have any questions from participants, so I guess we can close shortly. Maybe last few words from each one of you. Jeff, you first, and then Devdatta, and then we can close.
Yes, certainly. We view the market in India as a very unique market to enter for technology like ours, especially if we can modularize and bring a low-cost system to the marketplace for conversion of especially biomass into fuels like hydrogen, DME, and others that can be used in that market.
Thanks.
So one last word from my side would be, if you look at the entire focus of India is to go towards renewable energy and reduce our carbon emissions. And then the most easiest pathway, I would say, is to go for BioCNG, which we are anyway going right now, because we do not need to anything. We don't need to invent anything. Everything is there. Infrastructure is there. And it mixes so well with our natural gas grids. So we just a matter of scaling up, and I would think with the right kind of support from government side, it will take off.
Great. So from my side, I think the answer to our challenges, both as far as energy security, reliance, as well as decarbonization, is a mix of fuels. There's no silver bullet. We'll have to look at things on an end-use basis, on a commercial basis, and how we want to decarbonize in the future. So there's definitely space for all of the alternative technologies to grow as India itself is growing and the energy needs are growing. So there's a decade or two before our energy needs plateau out, and of course there's space for everyone in the intermediate. So that's it from our end. Thank you, Jeff. Thank you, Devdatta.
Thank you.
Have a good day, everyone, on the Gas World Tech session. Thank you very much.
Thank you.
Thank you, everyone. Bye.
Deepesh, back to you.
Thank you, sir, and distinguished speakers. It was once again a very insightful and informing session. So while we onboard the speakers for our next session, we will take a short break and look forward to meet you all in next 5 minutes. Thank you, everyone, once again.